Hi there, welcome to the second video on linear regression with Julia. In this video I will focus on building multiple linear regression models. If you are new here, I'm Alex Tantos and I am Assistant Professor of Text Linguistics and Computational Linguistics in Aristotle University of Thessaloniki. I've been using Python and R for my scientific computations for the last many years, but I've recently been letting myself get captivated by the benefits of Julia. One last side note I have to make before we move on to the meat of this video is that my videos are not meant to familiarize you with the statistical aspects of regression analysis. There are plenty of excellent resources out there that explain all the math details related to regression. However, I will be referring to some aspects of it wherever applicable to drive the point home. So, in this and the next series of videos, I plan to answer the following questions. First question is, how do I fit a multiple linear regression model in Julia? Multiple linear regression models, or MLR models from now on, can potentially be very complex. Bear in mind that MLR models, being extensions to simple linear regression models, allow you to examine the relationship between arbitrarily many independent or predictor variables and one dependent or response variable. For this reason, I will demonstrate how to build MLR models based on the simplest possible type of MLR models, namely those models that include two predictor variables, and I will cover all possible scenarios with these two predictor variables, namely when you have one numerical and one categorical predictor, two numerical predictors, and the last case scenario is when you have two categorical predictors. After you learn how to construct these MLR models, you will be able to build any type of MLR model using Julia, independently of the number and type of independent variables. I will also demonstrate how to use two of the available coding schemes of categorical variables in Julia and use them for building MLR models to respond to different kinds of research hypotheses related to the effects of the levels of the categorical predictors. I will then present a way of recovering in Julia the well-known and handy dot notation used in R for constructing formulas with the LM function and then wrap it up as a macro. And that is how this video will end. Fitting, interpreting, and exploiting MLR models for research purposes with Julia means that you will have to face a multitude of questions that I plan to answer in separate videos. For instance, how to evaluate a specific MLR model with Julia. And for answering that question, I will employ the most widely known error criteria in the next video, such as the root mean square error and the adjusted R-squared, among others, and I will show you how to extract the relevant indices of the model objects in Julia. Another question is how to automatically select the best subset of predictors to include in an MLR model with Julia using the most widely known selection strategies. Another question is how do I employ an MLR model object in Julia to make predictions? In other words, how do I predict the average response in the dependent variable for a given set of values of the predictor variables of the model using Julia? In future videos, I also plan to address more issues related to regression models, such as how to handle multicollinearity and how to deal with interaction terms and outliers. So, let's try to answer this video's questions. To begin with, let's have a look at the dataset we will be working on. The dataset is a randomly chosen sample of the Greek learner corpus, abbreviated as GLC, which is a corpus of reading productions made by second language learners of Greek. I also include a link in the video description below for you to browse through it if you're interested. The sample records 4 numerical and 2 categorical variables related to 100 second language learners of Greek. The numerical variables, GLC Part 1 to GLC Part 4, include the test scores of these 100 students on listening, reading, writing, and speaking tasks in Greek. The variable GLCL1 records the first or else the native language of the 100 speakers, and the variable GR communication skill records the students' self-assessment of their skills in communicating using the Greek language. Let's get a first good impression of the data within Julia. Here, I started Julia's interactive REPL and loaded all the necessary packages for running the code of the video, and available to download from a link in the description of the video below. Second step is to load the dataset stored in my GitHub account as a CSV file into a data frame. This can be done in a single step by using the download function that downloads the dataset into a temporary file, which will then be imported as a data frame with the read function of the CSV package. If you want to see the whole range of rows, you can use the show function and set the all rows and all calls arguments to true, as I did here. But let's take first things first. As you can see, the size function outputs the dimensions of the data frame, which in our case has 100 rows and 6 columns. Now, by default, the output of evaluating any data frame in Julia's REPL includes all column types, as you can see. Unlike what happens in R, where you would need to create an extra layer on top of data frames through dplyr tables to obtain that same output information. Before building any MLR model, you should obtain a good overview of what happens in the data, and possibly what could raise red flags, which essentially means two things. Trace any missing data and any inconveniences related to the distribution of the data, for instance outliers and different types of skewness. In the first case, assuming you found some missing data, you would need to decide what to do with them. Possible decisions include omitting the corresponding rows or following some common imputation techniques, and then proceed in transforming the data in case this is necessary. As I mentioned earlier, I intend to prepare separate videos on how to handle missing data and outliers. So, the describe function does all of that. Namely, it helps you reveal missing values or other potential problems. As you can see, apart from the mean of each column, it also provides information about the minimum, the median, and the maximum of the columns of a numerical type, as well as the number of unique values for the categorical variables, the number of missing cells that include the special value called missing in Julia. Missing is the singleton instance of the type missing, which is equivalent to NAs in R. Although in the relevant column of the output it shows that there is no missing value, you need to make sure that when importing the dataset from an CSV file, there are no hidden missing values in the dataset that were not translated into the missing data type in Julia, as it happens in GLC MLR. There is a string called NA that probably sneaked in while opening it from Excel or similar spreadsheet software. You can trace the rows that contain cells with the NA string either by using a functional and a bit verbose way with a filter function, or by indexing the data frame, which is pretty familiar to R users. The only difference being that, unlike in R, in Julia you need to add the vectorized dot operator in front of the double equal sign to apply the comparison element by element, or in Julia's terms, to broadcast it to all rows of the GR communication skill string column. Now, suppose you found such cases and you would like to replace these NA strings with Julia's special missing value. Here is a short, simple function that does that for all the rows of the data frame. For doing data manipulation on container-like objects, such as data frames, there are ready-made tools provided by packages such as query.jl. However, since the focus of this video is not data manipulation, I will stay to this simple function. As you can see, now the NA strings have been replaced by the correct Julia-compatible missing values. Now, Since there is only one such row and it does not cost much to remove it from the data frame, I will simply remove it. The function drop missing does exactly that. So let's have a look at the newer version of the data frame. Finally, let's inspect the type of elements in each of the columns. Notice that for some reason GLC part 1 is a variable that refers to values of type int64, whereas the rest of the numerical variables point to values of type float64. One of the performance tips in Julia documentation is that when creating functions that perform column-wise operations on objects of a container data type, such as data frames or arrays, whenever possible it helps to share with the compiler any knowledge about the type of the columns. That is why I prefer to convert all numerical variables in GLC part 1 into float64 with the convert function, so that all numerical variables are of the same type. As you can see from the output of the describe function, now we're good to go and ready to start building our first MLR objects in Julia. Let's jump right in the GLC MLR data frame and simulate the three possible scenarios when building an MLR model. Recall that in the first scenario, on the right-hand side of the formula, there are more than one predictor variables, whereas on the left-hand side there is one response variable. Note that in different scientific fields, predictor variables are also called independent or explanatory variables, while the response variable is also known as dependent variable. All these terms are used interchangeably, but essentially they mean the same. The second scenario applies to cases where the dependent variables are both numerical and categorical, and finally the third scenario holds when both predictor variables are categorical variables. Let's take the first scenario and fit an MLR model with two numerical predictor variables. Julia is particularly attractive to R users that would like to adopt it for fitting linear models, since the function lm in Julia, as I showed you in the previous video, is identical to R's lm function for fitting linear models. So, if you are an R user, you can very easily adapt to Julia's modeling strategy by following the R-style notation, using the lm function with its first argument being a formula and its second argument a data frame. The model GLC both numeric that I created here is a model of the learner's reading test scores that regress on the learner's writing and speaking scores. Julia's lm function is simply an alias for the function fit, and I suspect that the main reason for introducing the lm function in Julia is to make linear modeling friendly for R users, like me, that would like to get acquainted with Julia. So, the same model I built a minute ago can be expressed with the fit function as follows. The first argument declares the type of model to fit. The second and third fit arguments correspond to the first and second lm arguments respectively, so we have a formula and a data frame. Unlike Julia's lm alias function, R's lm function does not require a formula declaration through a macro in its first argument position. At the same time, Julia has good reasons to introduce the formula macro in the packages, stats models and GLM. I suspect the most important reason is that macro expansion happens during compilation, which means that macros are only executed once from where they are called. For instance, when a macro is called from within a function definition, it is expanded at the time that the function is defined, and then the function can be compiled. Before moving on to the next scenario, let's make a short detour to interpret the model that I just created. By building this model, we are interested in the effects of learners' performance in writing and speaking tasks on their listening task scores. Now, both p-values associated with the two predictors are greater than 0.05, which is the alpha significance level usually considered by the vast majority of studies and experiments. So, we should not reject the null hypothesis that the true slope for the performance in listening task scores is 0 when controlling for the learner's performance in writing and speaking tasks. Or, in other words, there is no evidence that the two predictors together are associated with the response variable. In the simple linear regression model of last video, I showed you how to extract the field names of a simple linear regression model object of type statsModel.tableRegressionModel with the field names function. Another very useful function that allows you to explore the available functions that are applicable to values of a specific data type, such as the table regression model or statistical model in our case, is methods with. What I appreciate about Julia is the fact that it provides such a rich inventory of functions that can extract meaningful pieces of information from regression model objects. I will make some time for these functions in the next video when I will be talking about model selection and evaluation. Let's head to the second scenario, and that is a scenario of building a model with numerical and categorical predictors. Here, GLC Mixed is a model object created in the same way as the GLC both numeric model, namely by juxtaposing the two variables with a plus sign. Now, let's take a pause and elaborate a bit on the coding of the categorical predictor. In other words, let's ask ourselves, how are the different levels of a categorical variable encoded so that the overall effect of the categorical variable on the response variable makes some sense in the context of regression? And then, how are the effects of the different levels of a categorical variable interpreted? And lastly, what kind of research questions can be answered by a coding scheme? The first question is answered through the various available coding schemes. A coding scheme is used for translating a categorical variable into a set of contrast variables. Contrast variables are some sort of elementary variables that come out of the categories of the categorical variable. The term contrast in contrast variables denotes a linear combination of these elementary variables that allow comparison of different treatments. Generally, categorical variables enter a regression analysis as a sequence of k-1 contrast variables for a categorical variable with k levels. Let's focus on the most common coding scheme, the dummy coding scheme, also known in machine learning as one-hot encoding. Julia, just like R, by default adopts the dummy coding scheme for adjusting categorical predictors in regression model building. This means that whenever you create a linear regression model and one or more of the predictors happen to be a categorical variable, then just keep in mind that if you do not define it otherwise, as I did for creating the GLC Mixed model, each of these variables translates to a series of dummy-coded contrast variables. For explicitly defining a coding scheme, you need to add the contrasts argument to the lm function and assign it a dictionary with the categorical variables as its keys and the coding scheme as their respective values. Here, I simply added the contrasts arguments with a dictionary that has the simple GLC L1 as its key and the dummy coding function as its value. As you can see, the output of GLC Mixed 2 is identical to the output of GLC Mixed, since the dummy coding is the default coding as I just mentioned. In dummy coding, each level of a categorical variable is compared or contrasted to a reference level. By default, the reference level is the first level of the categorical variable in alphabetical order. To drive the point home, let's have a look at the contrast matrix of the dummy-coded categorical variable of GLC-L1 in the GLC MLR data frame that has 9 levels. As you can see, GLC-L1 has 9 rows, whereby each row maps to a specific level of the categorical variable, namely a natural language in our case, and is signified by the presence of 1. The first row, however, is full of zeros and corresponds to the language of the reference level. All the rest of the languages are contrasted to the reference level. The transposed version of the contrast matrix takes part in the matrix multiplication of the design matrix with the coefficients matrix that results in the final matrix of the predicted response values created by the model. I know this may be too much to absorb for a beginner, and the subject of estimating the coefficients matrix as well as the creation of the design matrix requires a certain degree of acquaintance with linear algebra. I suggest that if you are interested in the mathematical details, you should go watch a linear algebra course, starting with the excellent playlist on the essence of linear algebra by Grant Sanderson's YouTube channel called 3 Blue 1 Brown. I will include a link to his channel in the end screen of this video. Apart from dummy coding, Julia supports various other coding schemes, such as effects coding, Helmert coding, sequential difference coding for ordinal variables. You can browse through the available coding schemes in the documentation of the Stats Models package. Different contrast schemes can help answer different types of research questions. For example, sometimes it is not particularly informative to compare groups to a reference level. You might want to compare between groups and the overall trend in your data. In that case, you would need to adopt the effects coding. Or you might want to compare between specific pairs of groups and create your own custom contrast coding scheme. You can do this with the function hypothesis coding in Julia, as you will see in a moment. In other words, choosing a coding scheme for a categorical predictor helps the regression coefficients of k-1 variables correspond to a set of linear hypotheses on the cell means. I will demonstrate how to use two of the coding schemes that Julia provides, the effects coding and the hypothesis coding. When the categorical variable is encoded with effects coding, the intercept represents the grand mean of all groups. The regression coefficients associated with the rest of the levels indicate the difference of each level to the grand mean. For instance, the estimate for the mean of the Arabic-speaking students is just 0.209 below the grand mean score. Now, for manually specifying contrasts through a hypothesis matrix, you can use the hypothesis coding function directly within the dictionary of the contrasts argument in the LM function. But before doing that, I need to specify my hypothesis matrix that expresses the set of hypotheses that I would like to test. Let's walk through an example in order to make the ideas more concrete. The first step is to create the hypothesis matrix that implements a series of hypotheses whereby each row corresponds to a contrast between two languages. The contrasted languages are set in the labels argument of the LM function. So, for testing the hypothesis that the difference between the average outcomes of Albanian and Arabic-speaking students is different from 0, the corresponding row of the hypothesis matrix would be the first one. Likewise, to test whether the difference between Arabic and Bulgarian is different from 0, the hypothesis vector would come from the second row of the hypothesis matrix. And that applies to a set of hypotheses that can be checked based on the contrasts defined in L1 diff hypothesis. Notice that the output does not include the variable names, but if I simply ignored the labels argument of the hypothesis coding function and adopted the deprecated behavior, the output would include the variable names. I guess that the updated version of the hypothesis coding function will sooner or later improve and also include variable names in the output. Moving to the last scenario, where the two predictor variables are both categorical, you can use everything you saw in the previous scenarios. The interpretation is slightly different, since now the intercept denotes the reference level of both categorical variables, and again the default coding scheme is dummy coding. As earlier, I could also construct a hypothesis matrix that will enter the hypothesis contrast coding of the second categorical variable, GR communication skill, which means that in this scenario, for which I would like to consider two sets of hypotheses for each categorical variable, I would have to prepare and use two hypothesis matrices. Here I use the hypothesis matrix L1 diff hypothesis I already created for GLC L1, and I now create L1 diff hypothesis GR for the second categorical variable GR communication skill. The last point I would like to share with you is how to integrate in Julia's LM function the dot symbol that is provided by R and is placed in the right hand side of a formula. The dot symbol aliases the set of all variables in a data frame that are considered independent variables in a regression model, except for the response variable that is placed on the left hand side of the formula. Let's make it clear with an example of how this works in R. I have already loaded the package rcall in the beginning of the script so that I can run R code within Julia's REPL and come across what I mean based on the well-known empty cars dataset. In R, I could build a linear model with a dot on the right-hand side of the formula that stands for every variable in empty cars other than WT, which stands for a car's weight. The dot notation is particularly useful when the number of predictor variables in an MLR model is high. Although Julia does not provide the dot notation, one can still recover the same functionality by constructing programmatically the formula that will host all predictor terms. The first step is to select all names of the data frame except for the one that is going to be our response variable. I decided to choose GLC part 1 as the response variable here. Last step is to construct programmatically the formula with all predictors on its right hand side and the response variable on its left hand side. Now I can build the linear regression model as usual with the constructed formula f as the first argument of the LM function. Since the dot functionality for including all variables in a data frame as regressor variables is definitely useful, one might consider to wrap up the programmatic construction of such a formula with a handy macro. A macro that would take all regressors and the dependent variable and output a formula term. Although macros are not so often used by developers and Julia users, I think this is one of the textbook cases in which creating a macro is useful. Here is a way of preparing a macro that wraps up the previous few lines of code for the dot functionality. The return statement is the generated expression I was looking for. Now, it is about time we put the macro into action. As you can see, it does what it is expected to. As it returns a formula expression, it should take its place as the first argument of the LM function. Here, the output, as expected, includes all the numerical predictor variables along with the contrast variables that represent each level of the categorical predictors of the model. That's all for now. Don't hesitate to drop a line on the comments section if you feel you have something to add on the content. The Julia code file presented in this video is already uploaded on GitHub, and you can go and fetch the link from the video description below.